In the endless darkness, 15 billion miles from Earth, Voyager 1, a spacecraft launched in 1977 for a 5-year mission, now faces a slow, irreversible shutdown. This is breaking. Voyager 1 shut off in deep space. NASA is preparing to switch off its historic cosmic ray instrument in February 2025, a move forced by a relentless and silent enemy. The probe's dwindling nuclear power falling by 4 watts every year. Each shutdown marks a farewell to decades of discovery and a gamble on whether any science can survive at the edge of interstellar space. But why is NASA willing to make such painful choices now? And what does this mean for the most distant explorer humanity has ever built? The heart of Voyager 1's endurance lies in its trio of radioisotope thermoelectric generators, a technology that converts the slow decay of plutonium-238 into electricity. At launch, these RTGs produced about 470 watts, enough to power a modest household appliance. Now, after nearly 5 decades, only 220 watts remain. The mathematics of radioactive decay are inescapable. Each year, the spacecraft's power supply drops by roughly 4 watts. A decline as predictable as it is relentless. This annual loss may seem trivial, but for a spacecraft that requires nearly 200 watts just to keep its antenna locked on Earth, every single watt is precious. The engineers at NASA's Jet Propulsion Laboratory have become expert stewards of this shrinking energy budget. Each instrument on board demands about 4 watts. A figure that once allowed for a broad spectrum of science but now forces hard choices. Power allocation is no longer about maximizing discovery, it's about survival. Systems and experiments that defined the mission's early triumphs have been systematically powered down. Cameras, spectrometers, and once essential sensors now sit silent, sacrificed to preserve the core functions that keep Voyager talking to Earth. The process is as meticulous as it is unforgiving. Every subsystem must justify its existence watt by watt. Heaters that once protected instruments from the cold are switched off, leaving vital electronics to endure temperatures far below freezing. Even the smallest inefficiencies are scrutinized. The mission's longevity depends on the engineer's ability to stretch each remaining watt, delaying the inevitable moment when the power falls below what is needed for even the most basic operations. This is the reality of deep space endurance, a slow descent measured not in miles but in watts, where the margin between contact and silence grows thinner with each passing year. On February the 25th, 2025, a command from Earth silenced Voyager 1's cosmic ray subsystem. This was not a technical failure, but a deliberate act, one calculated to stretch the probe's dwindling power supply just a little further. The cosmic ray subsystem, once the sentinel that confirmed Voyager's passage into interstellar space in 2012, had spent decades counting high-energy particles from the galaxy and the Sun. Its readings revealed the invisible boundaries of the heliosphere, mapped the flow of cosmic rays, and gave scientists their first direct evidence of the solar system's edge. Now its detectors have gone cold, sacrificed so that 3 other instruments might endure. Within weeks, Voyager 2 will follow suit, shutting down its low-energy charged particle instrument in March. Each instrument demands about 4 watts, a figure that once seemed trivial. Today, it is the difference between continued contact and silence. Only 3 of the original 10 science instruments will remain active on each spacecraft. The choices are not made lightly. Suzanne Dodd, Voyager's project manager, described the process as letting go of a scientific lifeline. She and her team weigh each decision with the knowledge that every shutdown means the loss of a unique window on the universe. Data no other probe will collect for decades, perhaps centuries. With every switch thrown, the mission contracts. The hope is to conserve enough power to keep at least 1 instrument alive into the 2030s. The cost is measured not just in watts, but in the knowledge left uncollected and in the quiet that follows when a once vital experiment falls silent amid the darkness between the stars. In November 2023, a steady stream of data from Voyager 1 suddenly turned to gibberish. Telemetry that once mapped the edge of the solar system became a jumble of empty codes, unreadable by any ground station on Earth. Engineers at the Jet Propulsion Laboratory faced a puzzle with no precedent. The spacecraft's flight data subsystem, responsible for packaging all science and engineering information, was now sending back patterns that defied every diagnostic tool. Bits and bytes arrived in sequences that made no logical sense, as if the probe's memory had been scrambled by some unseen force in the void. Specialists pored over the corrupted telemetry, searching for clues. They found that about 3% of the FDS memory had gone dark, likely due to a single failed chip, now useless after nearly 5 decades exposed to cosmic radiation. The loss was not random. The dead zone sat directly in the path of the software routines that handled Voyager's most basic functions. With each command sent, the probe responded in the same indecipherable tongue, confirming that the issue lay deep within its digital core. The challenge was more than technical. The memory chip was physically unreachable, and the software was written for a 1970s computer with just 68 kilobytes, less than a single modern email. Yet the team refused to accept defeat. They began to map the patterns of corruption, tracing which blocks of code had gone missing and which could be salvaged. The only hope was to relocate critical software routines, byte by byte, into surviving memory, a process that would require an unprecedented remote rewrite of the spacecraft's brain. For the first time since launch, Voyager's fate depended on the ability to rewire its mind from billions of miles away, with every command a high-stakes experiment in digital surgery. On March 20th, 2025, commands left Earth carrying a gamble as old as Voyager itself: revive the primary roll thrusters, devices untouched since 2004 and long written off as lost to the cold of deep space. The team at Jet Propulsion Laboratory had traced the original failure not to a mechanical breakdown, but to an elusive electrical switch, likely flipped by a circuit disturbance 2 decades earlier. If the heaters could be coaxed back to life, the thrusters might yet respond. The stakes were uncomfortably high. At Voyager's distance, every command travels for almost a day before reaching its target, and another day before any response is known. No room for second chances. Power was rationed with surgical precision. To warm the dormant thruster heaters, engineers temporarily shut down other subsystems, freeing just enough electricity to push the temperature above the threshold for safe ignition. The procedure required a delicate choreography. Activate the circuit, monitor the temperature rise, and be ready to abort if any anomaly appeared in the sparse telemetry streaming home. If the heaters failed to respond, or if a thruster valve stuck open, the spacecraft could tumble, its antenna drifting off Earth forever. Within 20 minutes of the scheduled activation, telemetry confirmed a sharp climb in heater temperature, evidence that the electrical reset had succeeded. For the first time in over 20 years, the primary roll thrusters were alive, ready to steady the spacecraft's gaze on home. This restoration meant more than redundancy. It bought precious time, allowing ground teams to alternate between thruster branches as fuel lines continued to narrow from decades of chemical residue. The success of this remote repair did not just preserve attitude control. It proved that even with vintage hardware and a shrinking power budget, ingenuity could still rewrite the rulebook for survival at the edge of the solar system. April the 20th, 2024. After months of garbled signals and uncertainty, the console monitors at Jet Propulsion Laboratory flickered with a familiar, ordered stream of numbers. A heartbeat restored. The telemetry signatures, once scrambled beyond recognition, now marched in clean, logical sequences. Each byte confirmed the spacecraft's mind had been reassembled, its software routines successfully relocated away from the damaged memory. Engineers watched as system status flags returned to green, the digital equivalent of a pulse after cardiac arrest. For the first time since November, the probe's engineering data aligned perfectly with expectations. Temperatures, voltages, and instrument states all reporting in the language of Earth. Across the control room, relief mingled with disbelief. A probe more than 15 billion miles away, running on less code than a pocket calculator, had accepted a remote brain transplant and survived. The team's months of forensic programming, each command a leap of faith across the void, had paid off. Voyager 1 was speaking clearly again. The revival of Voyager 1's primary role thrusters on March 20th, 2025 stands as a testament to the mission team's resolve. With the backup thrusters threatened by fuel line clogging, engineers gambled on heaters that had not worked since 2004. Power was so limited that every subsystem had to justify its draw. To attempt the reset, Dodd's team shut down non-essential circuits, freeing just enough electricity to coax warmth into the icy lines. Within minutes, a sharp rise in temperature signaled success. The thrusters fired, restoring full attitude control and preserving the spacecraft's ability to point its antenna toward Earth. For the propulsion team, this moment was both relief and reminder. Every system on Voyager now relies on ingenuity and careful stewardship. The spacecraft presses on, its future uncertain but its course steady, as engineers weigh each decision with the knowledge that every watt, every command, is a choice between silence and discovery. Voyager 1, launched on September 5, 1977, now travels more than 15 billion miles from Earth, powered by radioisotope generators that lose about 4 watts each year. In February 2025, NASA will shut down the cosmic ray subsystem, the first of Voyager's final 3 instruments, to preserve enough energy for the remaining science. Despite a major flight data system failure in late 2023, engineers restored contact with a software patch in April 2024, demonstrating technical ingenuity under extreme conditions. Yet, some questions remain. How long can the last instrument survive, and what new findings might still emerge from the edge of interstellar space? As of 2025, Voyager 1 continues to send data on magnetic fields and plasma, but each shutdown marks an irreversible step towards silence. According to mission records, its journey will end not with a sudden stop, but with the quiet fading of each signal, leaving the golden record to drift as Earth's message to the cosmos.